The main objective of this die press program is to help the user determine the optimum die assembly for any particular application. Die press program can do two main things. First, it can determine the optimum interference fit that the user should use between the components so that the stresses before and during the forming of the part are the minimum. This would give the maximum tool life for the components. The other thing that die press program can do is to help determine the dimensions or the outside diameter of the insert, middle insert, so that the assembly can take the maximum forming pressure. This program uses the classical theory of thick cylinders. It is not using any finite element analysis, and the reason why we use the classical theory is because it is much quicker to determine the level of stresses under different conditions so that the optimal solution can be determined in a much lesser time than it would take to do a finite element analysis. Now, before I go into this program, let me briefly explain to you the type of stresses that are there in a thick cylinder when it is subjected to internal pressure and the external pressure, because that's the basis on which this program determines the level of interference fit that would be needed to optimize the level of stresses. So in a die assembly, basically we may have two or three components. We have the innermost component where the pressure is applied from the forming. Like in this case, an extrusion die, we have the insert. And then we have the casing and then the interference between the two. So external pressure is applied on this insert. If I look at the stresses in this one component, let's say the insert, and there is a pressure acting from the inside from forming process, it ends up creating three types of stresses. The sigma A, which is the axial stress, sigma R, which is the radial stress in the direction of the pressure, and then sigma T, which is the tangential stress. Now we consider the stress to be tensile if it is positive, and compressive it is negative. When we apply the internal pressure, then the stresses inside a single cylinder, as they are shown here, we have the positive tensile tangential stress and the negative compressive radial stress at, let's say, the inside radius. Now the yield strength is the difference between the two using theory of plasticity. So the yield strength will be from this point to this point. That yield stress cannot exceed the yield strength of the material, because if it does exceed, then the material will deform plastically and would be of no use. So there is no opportunity to really optimize that in a single piece, because the stress is going to be based on whatever the pressure is. But in a two-piece assembly, it is possible to put an external pressure from the interference fit that can reduce the tangential stress, because the external pressure would put compressive stress, tangential stress, that would reduce the stresses on the inside. And through this compression or interference fit, we can now adjust the stresses in the insert as well as in the casing, so that both of the components have as low a level of stress as possible and none of them yield under the conditions of actual forming of the material. Using this basis, the die press program figures out what is the optimum interference pressure, and also the dimensions that will give us the maximum internal pressure that the assembly can take. So just an explanation of what you are seeing here on the graph. Along the x-axis, that is the radius. So we are plotting the radius along the x-axis, and we are plotting the stresses in the y direction. So the radius, so up to here, from this radius to this radius, we have the insert. So whatever is shown here between this radius and this radius pertains to the insert, the stresses that are being shown. Then anything from this radius to this radius is the casing. So whatever stresses are shown in this portion, that is the stresses in the casing. Now the positive side, that is the tensile stress, and the negative side on the y-axis is the compressive stress. So right now we are plotting it English units. So this is 35,000, 70,000, 105,000, 140,000, 175,000 psi. That is the scale on the positive side and the scale on the negative side. So the stresses themselves, the green color is for the radial stress. The red color is for the tangential stress, and the yellow is the difference between the tangential and the radial, that is in a way the effective stress. So the yellow curve here shows the effective stress. Between this portion insert, that's the effective stress distribution in the insert. And this portion, this is the effective stress distribution in the casing. So this red shows the distribution of tangential stress in the casing, and this red here shows the tangential stress distribution in the insert. In the insert, up to this point, this is the distribution of the radial stress, and this is the distribution of the radial stress in the casing. So if I look at this plot, it is this point that I would be concerned with. So this is the maximum effective stress in the casing at its inner surface, and that's at 175,000 psi. So if the limit of yield strength for this material of the casing is below 175, then this graph shows that that casing would yield, which is we definitely don't want, because once it yields, then it changes its dimension. Now this shows here is the desktop of the die press program. On the left hand side is the type of analysis that you can do. You can do a single ring analysis, a two-piece die assembly, determine the optimum dimension of the two-piece assembly, a three-piece assembly with the insert, middle insert, and the casing, and also determine the optimum dimensions of the insert OD and the middle insert. You can analyze the straight or the taper OD assembly of the insert. In the top portion here is where you would enter the information on the dimensions of the components as well as their material, and after that you would click on calculate to calculate the stresses, which will be shown here in this graphics area as it is being shown for a two-piece assembly, and also the results, the numeric values will be shown in the dialog box on the right. That's the scheme used to represent the results. If you want to save the results, you click on save, and this analysis then would be saved in a text file that you can always look back and see what the results were. When you are done, you click on done, and that basically takes you out of this analysis. Let me just show you for each of the case that it analyzed, just the pictures. I'm not going to go into details. That will be in a later video. We'll start with the single ring. If you press the single ring button, this is what comes up. I have just entered some of the dimensions. This shows the stresses. The green is the radial stress. The red here is the tangential stress, which is positive, tensile. The yellow here shows the effective stress, which is the difference between the tangential and the radial. This effective stress must stay below the yield strength of this material. Otherwise, the material would yield, and if it is hard, it's going to crack. Let me show you now the two ring. If you press the two ring press assembly, this is place where you enter the dimensions, which I have done, and you click on calculate, and you would see something like this to show you the stresses. When you perform the optimum dimensions analysis, basically you're going to enter the ID of the insert and OD of the casing, and it will show you the stresses with different dimensions of the insert, and allows you to pick the maximum, the dimensions which give you the maximum forming pressure. Now you would see from this graph that because I had put 200,000 as the yield strength for both the carbide and for the casing, it has taken it to that limit. So it also gives you what's the interference fit that you should put, as well as the dimensions that would allow the maximum pressure, which in this case is 160,000 psi. You can go with this assembly. If I press on the three-piece press assembly, then this is what comes up here for the info to be put in. I have put in certain numbers and click on calculate. That shows me the graph of stresses in the insert, middle insert, and the casing. And I can, like the two piece, I can also do the analysis to determine the optimum dimensions of these components so that the assembly would be able to take the maximum forming pressure at the bore of the insert. So far, I have shown you when the insert is straight, but if the insert was taper, then the analysis is very similar. I would select here the taper, and let's say go to the two ring press fit assembly. This would change somewhat. Now instead of the ID and OD, I would have the inside diameter of the insert and the length of the insert and the smaller diameter and the larger diameter. So in this picture here now, you can determine the stresses at any location, at the top, Here in this schematic, you can determine the stresses at the bottom or any other diameter in between, so that you would enter it here. So this here shows how the two ring press fit would look like if I have the taper insert selected. Now in the case of the taper insert, you can get the stresses at any location, at the top, at the bottom, or anywhere in the middle. So if I put 2.0, which is at the top, the smaller end of it, then these are the stresses. If I am interested in at the bottom where it is 2.1, I can put 2.1 here and recalculate it, and that gives me the stresses at the larger end. And at any other diameter, I can put that diameter here. Of course, it has to be between 2 and 2.1. I can recalculate the stresses. So this is how the taper die is included in the analysis. It can be done for the single, for the two ring assembly, as well as for the three component assembly. So these are different types of analysis that you can perform. We would go into more detail as to how you do each one of them, but this is basically what the die press program is.